This is a datum target symbol. The lower half contains the datum letter and target number. The top of the target symbol is left blank if the datum target is a point or line of contact. If the datum target is an area of contact, its diameter appears on top. The location of a datum target is specified by basic dimensions. Let's review what we've said about basic dimensions and datums. A basic dimension is a number which describes the theoretically exact size, shape, or location of a part feature. It's the basis on which acceptable variations are established for other dimensions. A datum is a theoretically exact point, axis, or plane from which the location or geometric characteristics of a part feature are measured. A datum is established from an actual part feature, called a datum feature. As many as 3 datums may be established to accurately define all the features on a part. Together, they form the datum reference frame, which corresponds to the planes formed by the X, Y, Z axes on many machines. For parts with irregular shapes, datums are established by datum targets. Datum targets represent places of contact between the datum feature and the inspection equipment or machine tooling. GD&T is rapidly becoming an indispensable tool that can impact productivity, quality, and profitability in the manufacturing world. The ability to understand and interpret this new technical language will help you keep pace with the changes it brings. In Unit 2 of this series, we'll identify and define the GD&T symbols and continue to explore some basic GD&T concepts. Open your application guide now to Unit 1, Review number 2. After completing this review, check your answers. If necessary, review the material in this unit before proceeding to the next one. Geometric dimensioning and tolerancing is a language for communicating design requirements. Like any language, it's made up of symbols, as well as rules for using them. In this unit, we'll take a closer look at the meaning of the GD&T symbols. We'll also cover some basic rules and principles which ensure that the symbols are interpreted the same way by everyone. Understanding the symbols and the principles behind them will bring you another step closer to reading and interpreting GD&T design requirements. As you'll recall, the GD&T symbols appear in a feature control frame on the drawing. This frame, for example, refers to a hole on the part. We'll see how this particular frame is interpreted, then go back and study each part of it in greater detail. The frame is divided into 3 compartments. The first compartment tells you the geometric characteristic controlling the hole. For example, this is the symbol for position. It locates the hole in relation to the datums. The tolerance compartment specifies the shape and size of the geometric tolerance zone for the hole. This symbol means that the hole's geometric tolerance zone is cylindrically shaped. The size of the geometric tolerance zone is 5 thousandths. So the axis of the hole must lie within a 5 thousandths tolerance zone for its entire length. This compartment may also contain a modifier. In this case, it's maximum material condition. Modifiers are sometimes used to further define the geometric tolerance zone specifications. The third compartment shows the datum references. Here, the hole is referenced to datums E, C, and F. Now that we've identified the individual components of this feature control frame, we can interpret it. The hull must be positioned within a 5,000 cylindrical tolerance zone at MMC with respect to datums E, C, and F. As you can see, the feature control frame conveys a lot of information about the hull. Let's look more closely now at each compartment. The first compartment identifies the geometric characteristic that's being specified. Geometric characteristics define the form and location of a feature, as well as its relationship to other features. The geometric characteristics fall into 5 categories: form, profile, orientation, runout, and location. The first category, form, controls the shape of a feature. It includes flatness, straightness, circularity, and cylindricity. These form tolerances are not referenced to a datum, but to a theoretically perfect counterpart of themselves. For example, suppose you're inspecting this surface for straightness using a dial indicator. The tolerance states that this surface may vary by 0.003 compared to the theoretically perfect straight reference surface on the right. The second category of geometric characteristics is profile. A profile is an outline of the feature from either a top, side, or front view. There are 2 types of profile: line and surface. Profile of line tolerances control a single line element. Profile of surface tolerances control all the elements on a part's surface. Profile tolerances define a boundary within which the surface or line profile must lie. They may be related to a datum or to a theoretically perfect geometric counterpart. The third category of geometric characteristics is orientation. Orientation tolerances control the perpendicularity, angularity, and parallelism of the features with respect to a datum. For example, this surface must be perpendicular to datum B. This surface feature must be at a 25-degree angle to datum B. When an orientation tolerance is used, the feature control frame must always contain a datum reference. The fourth category of geometric characteristics is runout. There are 2 types of runout: circular and total. A runout tolerance states how much a circular, conical, or cylindrical surface may vary from perfect form as it rotates 360 degrees around a datum axis. Circular runout is the variation in one cross-section. Total runout is the variation over the entire surface. Runout tolerances also require a datum reference in the feature control frame. The final category of geometric characteristics is location. Location tolerances state how much a feature or axis may vary from perfect location relative to a datum, a feature, or an axis. There are 2 types of location tolerances: position and concentricity. A position tolerance describes the exact location of a point, line, or plane of a feature with respect to a datum, a feature, or an axis. For example, the position of this slot is located with respect to datums A and C. Concentricity is when 2 or more features have a common axis. A concentricity tolerance controls the diameter of the cylindrical tolerance zone within which the axes of the concentric features must lie. For example, the axis of this feature must be concentric within a 3,000 cylindrical tolerance zone with respect to datum A. Both position and concentricity tolerances require a datum reference in the feature control frame. Let's pause to review. The first compartment of the feature control frame identifies the geometric characteristic that's being specified. Geometric characteristics control the form of a feature and its location with respect to other features. There are 5 categories of geometric characteristics: form, profile, orientation, runout, and location. Form tolerances control flatness, straightness, circularity, and cylindricity. Profile tolerances control the outline of an individual feature or the outline of an entire surface. Orientation tolerances control the perpendicularity, angularity, and parallelism of the feature with respect to a datum. Runout tolerances control how much a circular, conical, or cylindrical surface may vary from perfect form as it rotates 360 degrees around a datum axis. Location tolerances control the feature's position and concentricity with respect to a datum, a feature, or an axis. Open your application guide to Unit 2, Review Number 1. After completing the review, check your answers. If necessary, review the first part of this videotape before proceeding. Now that we've identified the geometric characteristic symbols, let's move on to the next compartment of the feature control frame. As you'll recall, the second compartment of the feature control frame contains information about the geometric tolerance zone. This is a diameter symbol. It signifies that the shape of the geometric tolerance zone around the feature is cylindrical. The diameter symbol and the resulting cylindrical tolerance zone apply only to holes and cylindrical shapes. When the diameter symbol does not appear in the feature control frame, then the shape of the tolerance zone will depend upon the geometric characteristic being specified. For example, if you're checking for flatness, the tolerance zone is formed by two parallel planes. For other geometric characteristics, the tolerance zone may be the distance between two straight parallel lines or two equally spaced boundaries. Having a tolerance zone that is the same shape as the feature itself is more realistic than the square or rectangular tolerance zone produced by the coordinate system. For example, in the coordinate system, the centers of these four holes are allowed to vary from true position by plus or minus 4 thousandths. The location of the holes may vary plus or minus 4 thousandths vertically and horizontally. This produces an 8,000 square tolerance zone. 3 of the hole centers fall outside the square tolerance zone. Therefore, they do not conform to the specification. As a result, the part is scrapped. This is unfortunate, since the part could be properly assembled with its mating part. The GD&T system, on the other hand, allows the location of the hole centers to vary within a cylindrical tolerance zone. The cylindrical tolerance zone rounds out to 11 thousandths, which is the diagonal measurement in the coordinate system. Now all the hole centers fall within the tolerance zone and the part is acceptable. The GD&T system with its cylindrical tolerance zone increases the acceptance area by more than half. As a result, scrap is reduced along with production costs. The next element in this compartment is the size of the tolerance zone. Here the cylindrical tolerance zone is 5 thousandths in diameter. If we were checking for flatness, the width of the tolerance zone between the two parallel planes would be 2 thousandths. The tolerance zone specifications may also include a modifier. A modifier further qualifies the tolerance zone specifications. You're already familiar with this modifier from Unit 1, maximum material condition. A maximum material condition exists when an external feature is at its upper tolerance limit, or when an internal feature is at its lower tolerance limit. For example, this shaft is at its maximum material condition when its size is 747 thousandths. The hole at MMC is 750 thousandths. When the maximum material condition symbol appears in the feature control frame, it signifies that the tolerance zone can increase in size as the feature moves from its maximum material condition to its least material condition. The result is a bonus tolerance. Let's show how a bonus tolerance is produced. The specification for this hole is 750 thousandths plus or minus 2 thousandths. In its maximum material condition, the hole would be 748 thousandths. As the size of the hole increases from its maximum material condition of 748 thousandths to its least material condition of 752 thousandths, each increase is added to the geometric tolerance of 5 thousandths. For example, if the hole increases in size from 748 thousandths to 749 thousandths, then that increase of 1 thousandth is added to the geometric tolerance zone, making it 6 thousandths. With each increase in hole size, a bonus tolerance would increase the geometric tolerance zone until the hole reached its least material condition. This maximum material condition principle recognizes the fact that when mating parts are at their maximum material condition, or worst case condition, the tolerance specified by the design engineer must be held to ensure proper assembly. However, as mating features approach their least material condition, they fit together more easily. So additional tolerance can be allowed without adversely affecting the part's assembly or functional requirements. You could compare the maximum material condition principle to a type of golf game where the size of the cup and ball varies. Think of the golf ball and cup as mating features and the path between them as a tolerance zone. In their maximum material condition, the cup is at its smallest and the ball at its largest. You must putt accurately within a narrow tolerance zone to sink the putt. Your margin for error is small. In their least material condition, the cup is at its largest and the ball at its smallest. This gives you a wider tolerance zone within which to sink the putt. Your margin for error has increased with the size of the hole. Another type of modifier is least material condition. As you'll recall,